Hello everyone, and welcome to another IB Physics video. Today we will be doing paper 1 from May 2022, Timezone 2. So let's get started. In this first question, it says that the radius of a circle is measured to be 10.0 plus or minus 0.5 centimeters. And it asks, what is the area of the circle? If you see all the options have 314 plus or minus and an absolute uncertainty for the uncertainty. So number one, let's get the area of the circle. The area is pi r squared. You can take pi as 3.14 multiplied by r squared. The radius is 10, so it's 100, which is 314. So that is fine. Just one note here. You have to be able to do this without a calculator, so of course this is not very hard, but you should still do it without a calculator. Next, to get the uncertainty, we get the relative uncertainty. Absolute uncertainty of the area over the area is equal to 2 times, because of the square, the absolute uncertainty of the radius, which is uncertainty of the radius divided by the radius. The uncertainty of the radius was 0.5. The radius is 10. This brings us to 1 over 10, which is 10% uncertainty for the area. But this is still relative uncertainty. It's 10% of 314, so the uncertainty would be plus or minus 31. The answer is D. For question 2, it says that two different experiments, P and Q, generate two sets of data to confirm the proportionality of variables x and y. The graphs for the data from P and Q are shown. The maximum and minimum gradient lines are shown for both sets of data. What is true about the systematic error and the uncertainty of the gradient when P is compared to Q? So one thing we have to notice first is that they will have different y-intercepts. And the y-intercept is usually related to the systematic error. And what that means is the systematic error for P will be a lot greater than the systematic error for Q. So if you go down, it will be greater for P, so it has to be either A or C. What about the uncertainty of the gradient? Well, if you look at the maximum and the minimum, the uncertainty of the gradient, you can make it be as maximum gradient minus the minimum gradient divided by 2. So if it's more spread out, there's a bigger uncertainty. So Q has a bigger uncertainty for the gradient. It has to be either C or D. The answer should be C. In the third question, question number 3, it says an object is sliding down a frictionless inclined plane. The object slides 1 meter during the first second, and it asks what distance will the object slide during the next second. So first, we're going to use the equation where S equals initial velocity times time plus 1/2 acceleration times time squared. First things first, it slides from rest, initial velocity is 0. Therefore, this term cancels. Just erase it to make it more simple. And we can make a table. In this table, we have time and displacement. At initial time 0, of course, displacement is 0. At t equals 1 second, we have t squared, or 1 squared is just 1, so just 1/2 a. At 2 seconds, it's 1/2 a times 2 squared, which is 4. And that just makes it 2a. During the first second, between 0 and 1, is 1 meters. So 1/2 a is equal to 1 meter. And of course, during the second second, it goes from 1/2 to 2a. And the difference here is going to be 3 over 2a, or, of course, since 1/2 a is 1, it's just going to be 3 meters. The answer is C. In question number 4, a ball is thrown upwards at time t equals 0. The graph shows the variation with time of the height of the ball. The ball returns to the initial height at time t. So here 0, at time t is capital T here, so it takes this much time to go all the way up and come all the way down. The question is, what is the height at h at time lowercase t, which is some random time in the middle? Let's label some of the important points of this graph. It's a parabola, so at the maximum height, the time would have been 1/2 this uppercase t. It takes the same amount of time to go from 0 to the maximum as it does to get from the maximum all the way back down. Next, we want to kind of know exactly how much time it takes to go from uppercase t to lowercase t, or from the maximum to here. So it would be this lowercase t minus this amount of time here, 1/2 uppercase t. Next, you have to know how long it takes to get from this point here all the way back down to 0, which is capital T. So that would be uppercase t minus lowercase t. And last thing, of course, the time between here, the maximum height, and going down, it's also 1/2 uppercase t. So there are several ways to solve this question. We're going to just talk about two of the major ones. The first one is you can use the Subert equation where displacement is initial velocity plus final velocity divided by 2. And this is the average velocity multiplied by the time it takes. Now, let's define what we're talking about here. We're talking about using this as the initial velocity and this as the final velocity, and the displacement from here to here would be the height h. So what we'll do is we'll change this displacement to h. Second, the amount of time it takes to get from this point to this point is uppercase T minus T here. So we will change this to uppercase T minus lowercase t. Next, you have to actually find the initial and final velocities, and this is relatively easy. The change in velocity is acceleration times the change in time. And to make it easier, you should probably use this maximum displacement point and maximum height as the where you start, because here the velocity is 0. Okay, so initial velocity u would be gravitational acceleration times lowercase t minus 1/2 uppercase t. And the final velocity, all the way here, would be gravitational acceleration times, and now it's from here to here, and this is just 1/2 uppercase t. Solving this, we get g lowercase t minus 1/2 uppercase t plus 1/2 gravitational acceleration 1/2 uppercase t. You'll notice that this term and this term will cancel out. Divide everything by 2 and multiply by uppercase t minus lowercase t. And this will give us 1/2 because of this term in the bottom, gravitational acceleration. The only term left up here is the lowercase t. And here we have uppercase t minus lowercase t. And the answer should be here, D. Now, we said we will also do a second way or second method to solve this problem. So what we'll do then is we'll try to get another Subert equation and use other Subert equation to get the same result. So first thing we're going to do is we're going to erase these equations here. So what's the second method that we're going to use? Well, if we were able to find the maximum height, all we would need to do is we would need to subtract this other height from the maximum up to here. So this maximum height, let's put it in blue, from here to here. Let's call it X max. And this other drop from here to here, let's call this S drop. Now we have a very simple equation, and what we'll do is we'll take H to be equal to the maximum height minus the drop. So how do you get the maximum height? Well, you could try to find the displacement from 0 all the way up. But what you can also do is we can also find how far it drops when it goes from maximum all the way to 0. It's almost the same thing. It's just a little bit easier to find the distance dropped because the initial velocity is 0 using, so S max would just be gravitational acceleration times 1/2 times the time squared, and the time is going to be from here to here 1/2 the total time, and you square it. Okay, what about the time for the drop? The time for the distance dropped would also be 1/2 gravitational acceleration. And now we're going to use this term for the drop, which is lowercase t minus 1/2 the total time t. And you square it. Using this, you would get 1/2 g 1/2 t squared minus 1/2 g t minus 1/2 uppercase t squared. And it's a little bit more work, more involved, but if you expand this and simplify, you will still get the same answer as D. And I'll leave that proof to you, and we'll go to the next question. So in question number 5, it says, a solid metal ball is dropped from a tower. The variation with time of the velocity of the ball is plotted. So here we have the velocity and time. You can see it's non-linear, so the acceleration is not constant. In the second part, the question says, a hollow metal ball with the same size is dropped from the same tower. The graph will represent the variation with time of the velocity of the hollow metal ball. So we have the graph of the solid metal ball, and we have to choose one of the other ones to be the one for this hollow metal one. Now, it's the same size, so the force of air resistance, or the force of drag, is going to be this same at the same velocity. But the hollow metal ball has less mass. So it is affected more by the force of drag. Even though the force of drag is the same at the same velocity, it will be accelerated upwards more because of the same drag, because it has less mass. So if it's accelerated upwards more, what will happen is it will not accelerate as fast downwards. So it will be stopped more by the air. So it cannot be A or B. Second, at the very beginning, the slope is still approximately g, the acceleration of Earth. So it has to be c. D has a different slope at the beginning. It would have different value for the gravitational acceleration of Earth, which should not happen. In question number 6, it says, a rocket has just been launched vertically from Earth. The image shows the free body diagram of the rocket. F sub 1 represents a larger force than F2. So here is F2, of course, should be the force of gravity, mg, right? in F1, if it's a rocket, there's exhaust gases going downwards. It's a force of the exhaust gases on the rocket, right? And the question says, which force pairs with F1 and which force pairs with F2? And what we should probably do is we should probably make a sentence of what these forces are doing and what is acting on what. So we have one sentence for F1. F2 being the gravitational force or weight is the gravitational force of Earth on the rocket. And the way you get the equal and opposite force according to Newton's third law is you take the noun and object, and you switch them. So in case of F1, it will be the force of the rocket on the exhaust gas. So force of the rocket on exhaust gases. The answer should be either A or B. What about the force 2? We said gravitational force of the Earth on the rocket. Let's switch Earth and rocket. So it's the gravitational force of the rocket on the Earth. So it should be either B or D. Of course, that means the answer should be B. In question number 7, a book of mass lowercase m lies on top of a table of mass uppercase M that rolls freely along the ground. The coefficient of friction between the book and the table is mu. A person is pushing the rolling table. What is the maximum acceleration of the table so that the book does not slide backwards relative to the table? Number 1, what this basically also means is they both have the same acceleration. So whatever acceleration she pushes the cart, the book should also have the same acceleration. But in order for the book to accelerate, it needs a force of static friction. The person pushing on the trolley is putting a force on the trolley with accelerated trolley. Some other force must be acting on the book to accelerate it. That is a static friction force, Fs, and there's a maximum value to this. Of course, the maximum value is the coefficient of static friction times the normal force R, which in this case, being horizontally flat, would be just mg. Now, if that is the net force on the book and the maximum net force, the maximum acceleration, which is the force over the mass, would just be mu g. The answer should be B. In the following question, question number 8, there's 2 blocks of different masses that are released from identical springs of elastic constant, 100 newtons per meter. Initially, this spring is compressed at a distance of 0.1 meters. Block X has a mass of 1 kilogram, so let's write it down. 1 kilogram from block X. And block Y has a mass of 0.25 kilograms. What are the velocities of the blocks when they leave the springs? Now, these springs are not connected to each other. They're completely separate. They have the same spring constant and same compression or displacement. That means they should have the same amount of energy. The energy stored, or the elastic potential energy, is of course 1/2 kx squared, which is 1/2 times 100 times 0.1 squared. 100 times 0.1 squared is just 1. So let's just put this as 0.5. The kinetic energy of both these blocks have to be identical to the elastic potential energy because that's where it came from. Kinetic energy being 1/2 mv squared means that the velocity has to be the square root. So 1/2 times 0.5 is just 1. So it's 1 over the mass. In this case, for block X, the mass is 1 kilogram. 1 over 1 is 1, so it has to be 1 meter per second. And for block Y, we can calculate this. It cannot be 1 meter per second, so by default, it should be 2 meters per second. But if you calculate this, 1 divided by 0.25 would be 1 over 1/4, which is just 4. And the square root of 4 is 2, which makes sense. The answer should be C. For question number 9, it asks, what is true for an ideal gas? And, well, the most easily remembered equation from chapter 3 about gases is PV equals nRT. The second equation, which you should also know, although it's not in the physics booklet, is PV equals capital N, which is number of molecules, as opposed to lowercase n, which is number of moles, multiplied by the Boltzmann constant, K sub B, and the temperature. So PV equals nRT, or PV equals NKBT. And if you know these two equations, these two parts are the same, so you should know that the answer should be A as well. If you do forget about this, there's another way you can get this without memorizing these equations. If you look in your physics booklets, we have the average kinetic energy is 3 over 2, the Boltzmann constant times the temperature, or 3 over 2, the ideal gas constant divided by Avogadro's number times the temperature. This would mean that this, the Boltzmann constant, and the gas constant divided by Avogadro's number are equal to each other. So Boltzmann constant is equal to gas constant over Avogadro's number. The temperature on both sides doesn't really matter too much, so I'm not going to write that part. But last part here, you should also add to this that the number of moles, according to the physics booklet, is the number of molecules divided by Avogadro's number. Combining these two equations should still give you the same result, A. What about question number 10? Question number 10 says, which assumption is part of the molecular kinetic model of ideal gases? I'm going to highlight the word assumption because there are several assumptions that you should know about ideal gases. Some of these are technically correct from the options, but they are not assumptions for ideal gases. For instance, A, the work done on the system equals to the change in kinetic energy of the system. This is from thermodynamics, and technically it is true, but it is not an assumption. It's just a result of how gases and work is calculated. So it is not going to be A, not an assumption. B, the volume of gas results from adding the volume of the individual molecules. And recall, one of the assumptions is the volume of the molecules must be negligible. The gas is mostly empty space, so it cannot be B. C, a gas is made up of tiny identical particles in constant motion. Tiny, of course, is a result of the volumes being negligible. They're in constant random motion. This is another one of the assumptions. The answer is indeed C. D, all particles in a gas have kinetic and potential energy. In a gas, at least in a ideal gas, they do have kinetic energy, of course, because of the temperature. They're bouncing around. But the intermolecular force between the atoms is 0. That means that the work, which is the force times displacement, is also 0, which means that the potential energy is also 0. So ideal gases do not have potential energy, which means D is incorrect. Question number 11. It reads that water at room temperature is placed in the freezer. The specific capacity of water is twice the specific capacity of ice. Assume that the thermal energy is transferred from the water at a constant rate. Which graph shows the variation with time of the temperatures of the water? So the only hint here is the heat capacity of water is 2 times the specific heat capacity of ice. So let's translate this. It's harder to change the temperature of the water. Which also means you need to either remove more heat or give it more heat in order to have the same change in temperature. So, if you look at these graphs, we have water going down, it freezes, and then becomes ice, and the ice temperature goes down. They cannot have the same slope because it should be harder to change the temperature of water. So, if you look at B, you have the slope of water is some value, and the slope of the temperature of ice is a lot steeper, which means it's easier to change the temperature of the water, of the ice, which means the answer is indeed B. Again, C is incorrect because they have both the same slope. It's just as hard to change the temperature of ice in the water. And D, the water having a steeper slope means it's also easier to change the temperature of the water, so it's not going to be D. One last thing you probably want to do is, well, how do you prove that the heat capacity is related to the slope of the temperature? Well, let's go back to the equation. You might probably memorize as Q equals mc delta T. But temperature is in the y-axis, so we should probably put the temperature in the left-hand side of the equation. And then we have time in the x-axis. Time is related to the heat because power times time is the heat Q. So in the other side of the equation we have mc over power times time. Actually, no. Power times time over mc. There we go. Sorry about that. Now, finally, we said time is in the x-axis. And we can do is, let's replace this with the y-axis. This is in the y-axis, but y is equal to. Time is in the x-axis, so that would be x. Everything else in this equation, power divided by mass and heat capacity, would be m, the slope. So we should put actually slope here like this, because m is all occupied as a mass. Increasing heat capacity makes the slope smaller. Decreasing heat capacity makes the slope more steep. Question number 12. It says a particle undergoes simple harmonic motion. Which quantities of the motion can be simultaneously zero? Now, there's one very simple thing you should probably use for this problem here, and that is that the displacement is proportional to the force in opposite direction, or displacement is proportional to the acceleration but opposite direction. One thing you should be very careful of, just because they're opposite directions does not mean it's inversely proportional. Inversely proportional is 1 over that value. So, if x equals 0, acceleration is 0. So the answer should be B. And if you kind of think about it like this also, the object goes back and forth like that. There's going to be a maximum displacement. At the maximum displacement, which is called the amplitude, it has to stop and turn around. So here, velocity is 0. When the displacement is 0, it's passing really fast through the equilibrium position, so the velocity is at the maximum. So it's 0 displacement, maximum velocity. It cannot be A. At 0 acceleration, 0 displacement is maximum velocity, so it cannot be C. And displacement, velocity, and acceleration cannot all be 0 at the same time. It cannot be D. Question 13. A wave travels along a string. Graph M, this first graph here, shows the variation with time of the displacement of a point X on the string. Graph N, down here, shows the variation with distance of the displacement of the string. PQ and RS are marked in the graphs. So graph M has displacement in time. Graph N has displacement and distance. And the question says, what is the speed of the wave? Now, to make this more simple, it feels very complicated, but the speed is distance over time. How do you get the distance? Well, you go to the distance graph and you get RS is a distance, and the amount of time it takes to move that distance would be PQ, because it's from the time graph. So the speed would be RS over PQ. That would be C, RS over PQ. Number 14. The refractive index of glass is 3/2, and the refractive index of water is 4/3. What is the critical angle for light traveling from glass to the water? First things first. Change these to decimals. 1.5, 1.33. Just to make it easier to see that the glass has a higher index of refraction and the water has a lower index of refraction. And what usually happens is, if you have the light has to be coming from here and bounce off the high one to have total internal reflection, which is why you need to get a critical angle. And we're going to use Snell's law. Index refraction of water times sine angle incident on the interface of the water. Index refraction of the glass, sine the angle incident to the normal or glass here. So you start in the glass, so this is going to be the critical angle. You're trying to leave the water and go into the water, but at the critical angle, this is 90 degrees, so sine of 90 degrees, which is basically just 1. In this refraction of the water is 1.33. And let's actually keep it as a fraction because it's 4/3. You can use a calculator. Equals, in this refraction of the glass, which is 3/2. And we're going to get sine of the critical angle is 8/9. And you do the arc sine for both sides. The angle for the critical angle should be D in arc sine 8/9. Next question. The next question, number 15, reads, unpolarized light with an intensity of 320 watts per square meter goes through a polarizer and an analyzer originally aligned parallel to the polarizer. First things first, the analyzer is just another polarizer. The only difference is we can use it's a polarizer that can rotate, and of course after you rotate it you can measure the intensity here. Okay, second part, the analyzer is rotated through an angle of 30 degrees and it gives you the cosine of the angle. So what has to happen here? Number one, always remember, it's unpolarized first. And let's say this is overage intensity I0. After the polarizer, let's call this intensity I1. After the analyzer, let's call this intensity I2. I1 is always going to be 1/2 the initial one because it's unpolarized going through a polarizer. So what about I2? This is going to be I1, the previous intensity, times cosine square theta according to Malus's law. Cosine of 30 degrees is the square root of 3 over 2. If you square it, you get 3 over 4. I1 is 1/2 of the original intensity. And all you have to do now is you have to put 320 here where the I0 is, which is the original intensity, which would be 320 times 3 divided by 4, which would be 80 times 3, or 40 times 3. The answer should be A. Next, number 16, it says 4 particles, 2 of charge positive Q and 2 of charge negative Q, are positioned as shown at a particle P. This is called particle P as red. It has a positive charge and is placed in the y-axis. What is the direction of the net electrostatic force on this particle? So, it's positive charge. So let's color code this. Say this positive charge, positive Q in green, is going to push it away, it repels. So let's do this. Next, the other positive charge is closer, but it's also positive, so it's going to repel it, and it has a bigger force. Next, this negative charge here is an attractive force, so it's go like that. And finally, this other negative charge in black, let's do this. Now, might have messed up the angles just a little bit here. Actually, this should be smaller. This should be bigger. And this is further away, so it's smaller. So this vector here and this vector here will add up. The vertical components will cancel out, and it's just going to be to the left. In fact, if you add all these 4 vectors, the net result would just be that you have a force to the left. The answer should be D. In number 17, it says a battery of negligible internal resistance is connected to the lamp. A second identical lamp is added in series. What is the change in the potential difference across the first lamp? And what is the change in the output power of the battery? So, first things first, if you add something else in series, it's like adding another resistor. The total resistance doubles. Next, if the total resistance doubles, the total current is halved. And finally, the power is equal to the voltage. In this case, the total voltage is the EMF times the current. The current is halved, so the output power of the battery decreases. What about the change in the potential difference of the first lamp? Well, let's draw the voltage graph for the circuit. So we have the battery here, we have the first lamp. Actually, let's put it a little bit more separated. So what happens if the lamp is by itself? Well, first you have 0 voltage, the battery increases the voltage, goes out. Now the voltage drops when it meets a resistor, so it goes down like that. That's a big drop. In fact, the drop in the first lamp is equal to the EMF if nothing else is connected. And what happens if you add a second lamp? Well, the total voltage is the same. So you start still 0. The battery increases the voltage by the same amount. The only difference is now it drops half the voltage in the first lamp, and then the second half of the voltage is dropped in the second lamp. So the change in potential difference, or the potential difference, decreases. The answer is A. Number 18. A circuit consists of a cell of EMF E equals 3 volts. There are 4 resistors connected as shown. R1 and R4 are 1 ohms. R2 and R3 are 2 ohms. What is the voltmeter reading? First things first, the voltmeter should not be considered as part of the circuit. Ideally, there's no current going through the voltmeter. So if we just erase it for now, and you can kind of reimagine this circuit as just being the battery, and there's 2 parallel paths. Okay. Let's take the top path to be this path here, and the bottom path is this path here. So in the bottom path we have R1, which is 1 ohms. We have R3, which is 2 ohms. And in the green path, we have R2, which is 2 ohms, and we have R4, which is 1 ohm. And it's a little bit easier to imagine like this. The total resistance, of course, there's 3 ohms and 3 ohms, same as top and bottom parallels. It's going to be 1.5 ohms total, which means the total current is 2 amperes because it's 3 volts here. Second, it's 2 amperes. Half of it goes to the top side, half of it goes to the bottom side. So let's say 1 amp on both sides. And finally, why are we doing this? Because you literally have connected a point here, and a point here, and you want to measure what is the voltage difference between these 2 points. Now, normally if you use a voltmeter, you want to know what the voltage is doing when it crosses one specific resistor. So it's a little bit unintuitive to imagine what happens when you do this. But again, the voltmeter measures the differences in the voltages. So if we're to draw the voltage graph, let's say you're going to take the green path. In the green path, it goes up 3 volts, so let's go up 3 volts here. Here, the voltage drop is IR. I is 1 ampere, R is 2 ohms, so just 2 volts. So it goes 2 volts, 2/3 down, and then 1 volt drop in the second resistor. Let's put some numbers here. 0 volts at the beginning, 3 volts all the way up here. It drops 2 volts, so it goes down to 1 volt. And here, another drop of 1 volt, so it goes down to 0 again. What about the blue path? In the blue path, it first drops by 1 volt. So it goes 0, it goes also to 3 volts, it drops only 1 volt. So it drops to 2 here, and then drops back down to 0. When you connected this voltmeter, you're measuring 2 volts on one side and 1 volt on the other side, and the difference is 1 volt between those two sides. Okay, let's go down to the next question. Okay, number 19 is a bit tricky because I've seen several people try to answer this question incorrectly while trying to get the solution. It reads, the coil of a direct current electric motor is turning with a period of T. At T equals 0, the coil is in the position shown in the diagram. Assume the magnetic field is uniform across the coil. Which graph shows the variation with time of the force exerted on the section XY of the coil during one complete turn? Okay, first, let's assume the current is running this way. So it's going to go here, and this goes in this direction in XY. In the other side, it goes in the opposite direction. So if the current is going in this direction XY, let's see, the magnetic fields go from north to south, like so. And these are perpendicular, right? So we have current, index finger, we have magnetic field as middle finger, the thumb is a force, there's a force upwards, like so. And the other side, the current is the opposite direction, so the force is going down. Now, the first thing you have to notice here is it says it's uniform magnetic field. So when you get the equation for the magnetic force, it's magnetic field strength times the current I times the length times the sine of the angle between the field and the current. They have to be 90 degrees, so it's a maximum force. If they're in the same direction, the angle is 0, the force is 0. So here, the magnetic field is always the same. The current is the same in both cases, in all cases, and the length is the same in all cases. The force should not change, which is a tad bit unintuitive because I think one of the graphs you've shown in chapter 11 shows a sinusoidal graph. And in fact, it would be similar to sinusoidal graph if it were not uniform and if there were other considerations to do as well. But here, notice that A and B have that where it's not sinusoidal, it's always uniform. So it cannot be C and it cannot be D. Second thing is, if you go back to the force directions, while it's in one side, it's upwards, and the other side, it's downwards. And because they're opposite directions, the answer should be A. Now, the last thing of the reason it has to be like this, it's not sinusoidal, it's just straight lines, is the angle is not changing, first of all. You might think, oh, well, isn't it rotating? Yes, but it's not the angle of rotation, it's the angle between this field, which is always going from north to south, and it's the angle with the wire, which is always perpendicular. Just because it rotates doesn't change that angle. So we have, as you see here, wire, field, changing this like this doesn't change the angle between them, right? In one side, it's up, which makes it positive. The other side is negative, down. So here's one other thing you should probably know. You do not really learn about torque in the regular syllabus unless you do the option. The torque would be sinusoidal because the torque changes with the angle. In this case, it's only the force, so the force does not change. Okay, next, number 20. Number 20 says, a satellite is orbiting Earth on a circular path at constant speed. 3 statements about the resultant force on the satellite are: 1. It is equal to the gravitational force of attraction on the satellite. Yes. There's only one force, right? And that force is gravitational force. So, the resultant, which is net, you add all the forces, there's only one, they have to be equal. So, okay, good. 2. The resultant force is equal to the mass of the satellite multiplied by its acceleration. Yeah, F equals ma. In this case, the gravitational acceleration, g, would be m times gravitational acceleration, gravitational constant, mass of the planet over r squared, and lo and behold, this is still the equation for gravitational force. Okay, let's highlight this m and this m here. Gm over r squared is the gravitational field or the gravitational acceleration. So that works out. Number 3, it is equal to the centripetal force on the satellite. Centripetal force is a condition. You ask yourself, is it moving in a circle? If the answer is yes, then, so if yes, then net force also equals mv squared over r, centripetal force. Satellites go in the circles, which is assumed in the IB syllabus, so it has to equal to the centripetal force. The answer is all 3, D. Number 21. An astronaut is orbiting Earth in a spaceship. Why does the astronaut experience weightlessness? A, the astronaut is outside the gravitational field of the Earth, and that is incorrect. If they were not moving in a circle, they will still fall, and it is because of the gravitational field. B, the acceleration of the astronaut is the same as the acceleration of the spaceship. That is correct. Let's go back to that one later. The spaceship is traveling at high speed, tangentially to the orbit. This is not the correct answer, even though it might seem like it is. The gravitational field is 0 at that point. The gravitational field is not 0. Remember, gravitational field is mass of the planet divided by the distance squared. This technically is never equal to 0. Okay, what about B? The astronaut is accelerating. He is falling. The reason they feel weightless is because the feeling of having weight is actually the normal force. If you stand up, what you feel on the heels of your feet is the floor pushing up on you. If you were to jump off a building or a bungee jump, you will still be feeling the force. You will still be subject to the force of gravity, but if you don't have a normal force, you don't feel it. If you accelerate the spaceship at the same acceleration as the astronaut, you do not need additional normal forces to keep that astronaut in the same path. So because there's no normal force, yes, there is no feeling of weight, which means they will feel weightless. If they were moving too fast or too slow, you would need a certain amount of normal force, which is why C is incorrect. Number 22. White light is emitted from a hot filament. The light passes through hydrogen gas at low pressure and then through a diffraction grating onto a screen. A pattern of lines against the background appears on the screen. What is the appearance of the lines and background on the screen? And you have 2 choices for each. Lines either dark or white. The background is either black or colored. Okay, so what happens? First, white light is white because it's a mix of all wavelengths and all colors. Of course, it's a bit wrong to say mixed about colors, because technically colors are only between inside the visible spectrum, which is 400 to 700 nanometers. But real light includes infrared, which is invisible, and ultraviolet, which is also invisible. So white light is actually what we call continuous spectrum. It contains all the colors. You would see it as a rainbow. And it passes through hydrogen gas. When it passes through hydrogen gas, it only absorbs certain wavelengths. So you have all the wavelengths, all the colors, and only certain wavelengths are absorbed. So you have lines where they disappear and they become dark. So lines are dark. And the rest of the background is colored, because the diffraction grating acts like a prism, or similar to a prism. It just separates all the colors so you can see all the different wavelengths in different places. This is incidentally called the absorption spectrum. Is the exact opposite of the emission spectrum. And the emission spectrum has dark background and colored lines. Number 23. Three statements about electrons are: number 1, electrons interact through virtual photons. Number 2, electrons interact through gluons. Number 3, electrons interact through particles, omega and Z. Which statements identify the particles mediating the forces experienced by electrons? So first of all, particles mediating forces, these are the exchange particles. So electrons can use photons, which is they can emit photons, they can absorb photons, and they can also emit and absorb omega and Z bosons, which is beta plus and beta minus decay. They cannot interact with gluons, so gluons only interact with quark. So the answer should be 1 and 3, B. And number 24, a neutron is absorbed by a nucleus of uranium-235. One possible outcome is the production of two nuclides, barium-144 and krypton-89. How many neutrons are released in this reaction? You should have this memorized. Always 3 are released. But there's a trick to this question. If you just use, 235, 144, and 89. Okay, let's put 144 plus 89, and you get 233. You might think, well, the difference between 235 and 233 is 2. You might have released just 2 neutrons, which is incorrect. And the reason it's incorrect is because you also absorbed the neutron, so you added 1 there. Absorbing the neutron makes it go to 236, and it releases 3 neutrons, D. Number 25. A radioactive nuclide X decays into nuclide Y. The graph shows the variation with time of the activity A of X. X and Y have the same nucleon number. What is true about nuclide X? So first of all, it's X becoming Y. They have the same nucleate number. The only way this is possible is that this is beta decay. It's either a neutron becoming a proton or a proton becoming a neutron. It doesn't really matter which one it is. If you had alpha decay, what would happen is alpha decay reduces both the number of neutrons and the number of protons, and the total number of nuclei goes down by 4. So it cannot be alpha. That immediately rules out A and B. What is the next part? Okay. So C and D are both about beta particles, which is fine. It says half-life. Well, literally, you can see the graph. It starts at 1, 2, 3, 4, 5, 6 units. And then you look for the point where it has 3 units. 2T Half-life is 2T. Answer should be D. Just to confirm, F4T is 1/2 again, which is 1.5. Yeah, that works out. You should always check this too, because you might have cases where the background radiation has to be taken into account. 26. Photovoltaic cells and solar heating panels are used to transfer electromagnetic energy of the sun's rays into their other forms of energy. What is the form of energy in which solar energy is transferred in photovoltaic and solar heating panels? You have two options: photovoltaic, electric, or thermal, and two options for solar heating, thermal and electric. And the answer is, of course, in the name. Voltage has to be related to electricity. Heating has to be related to thermal. The answer, of course, is A. (27) Three statements about fossil fuels are: 1. There's a finite amount of fossil fuels on Earth. Well, that's true. 2. The transfer of energy from fossil fuels increases the concentration of CO2 in the atmosphere. Well, yeah, if you burn them, you produce carbon dioxide. That is true as well. 3. The geographic distribution of fossil fuels is uneven, which has led to economic inequalities. This is technically not part of physics, but yes, there's some countries have more fossil fuels. This is also correct. The answer is D. Number 28. The age of the Earth is about 4.5 times 10 to the 9 years. What area of physics provides experimental evidence for this conclusion? Remember, half-lives are very useful when you want to measure time. So the answer should be C, radioactivity. Newtonian mechanics is really useful when you want to find velocities and distances and time. Optics is useful if you want to have calculated resolution, or lenses. Electromagnetism, well, not related to time in any way, so it has to be C. Number 29. A simple pendulum has a period T on Earth. The pendulum is taken to the moon, where the gravitational field strength is 1/6 that of the Earth. What is the time period of the pendulum on the moon? Very simply, open up your physics booklets. You'll see that the period of the pendulum is 2 pi times the square root of the length over the gravitational acceleration. Making the gravitational acceleration 1/6 will make the period square root of 6 times greater. The answer is A. Number 30. In two different experiments, white light is passed through a single slit and then is either refracted through a prism or diffracted through a diffraction grating. The prism produces a band of colors M to N. The diffraction grating produces a first-order spectrum P to Q. What are the colors observed at M and P? Well, first of all, it's always going to be the red or violet, right? That's the only two choices. And what you should probably do is, if you don't memorize this yet, you have to know the relative lengths. Red, it has a wavelength of 700 nanometers. Violet of 400 nanometers. You should probably know the numbers, even though they say you shouldn't memorize it. Or you don't need to memorize it, but you should probably know them. Red is longer. Wavelength, violet is shorter. And what happens is they act differently in prisms and diffraction gratings. In diffraction gratings, you have d sine theta equals n lambda, which means if you have a longer wavelength, you have a bigger angle. In this case, it only asks for P, bigger angle, longer wavelength, it has to be red. What about prisms? In prisms, longer wavelengths are less affected by the refraction, right? So they have lower refractive indices. so less affected. That means they bend less. Look for N. M bends less. It is also a longer wavelength. It is also red. The answer should be A. Number 31. A train is sounding its whistle when approaching a train station. So the train is a moving source. Three statements about the sound received by a station observer at the station are: 1. Frequency received is higher than the frequency emitted by the train. Are they moving towards each other? Yes, they are moving towards each other. The frequency is indeed higher. This is correct. Number 2, the wavelength received is longer than the wavelength emitted by the train. This only happens if the source is moving. The source is moving, so if you look at the wave fronts, they get bunched up in the front. The wavelength is smaller. Indeed, the wavelength is shorter. Actually, it should be shorter, not longer. So it's wrong. Number 3, the speed of the wave is not affected by the motion of the train. That is correct. Speed of the wave is not depending on the motion of the source. So the answer should be 1 and 3. Number 32. 2 positive and 2 negative charges are located at the coordinates of a square as shown. Point X is the center of the square. That means they're all the same distance. What is the value of the electric field E and the electric potential V at the center X due to the 4 charges? So let's color code this. Green, blue, red, and let's add violet, violet. So let's do the electric fields. Positive, the electric field is going to be away from this. Red, negative, so the electric field is towards the negative. Green, negative, towards the negative. And blue, positive, so it's away from it. They're all the same size, they're all opposite directions, they all cancel out. The electric field is 0. What about the potential? You say, okay, potential is not a vector. You just add them normally, but a positive charge will have a positive potential, positive V. Negative charge has negative potential, negative V. Positive potential, negative potential. They are all the same distance and all the same charge. All these values are the same. Plus, minus, they cancel out, becomes 0 again. Well, the answer is A. (33) The graph shows the variation with distance r of the electric potential V from a charge Q. What is the electric field strength at the distance S? So 1, potential is positive, it's a positive charge. Next, if you go to topic 10, electric field strength is negative. The change in voltage over the change in distance, this is literally slope here. So it's not the area, it's a gradient. Notice there's a negative sign. It's a negative of the gradient. The answer should be D. And here's the reason why. If you have a positive charge here, at some point here, the field will be away from it. To the right is positive, right? Look at the gradient. The gradient is negative. This is why you need to change the sign. Just a convention to make sure that the directions are the same. Which 2 features are necessary for the operation of a transformer? Feature 1, there's 2 choices. There's either electrical connection between the primary and secondary coils and the magnetic interaction between primary and secondary coils. Well, first things first, Having an electrical connection means there's current going through them. If you recall, the whole point of a transformer is you have a coil, and then you have a second coil. They're not connected to each other. There is what's it called? A core to transfer the magnetic fields from one side to the other. So it has to be magnetic, not electrical. Number two, this only works with alternating currents because in order to get the EMF on the other side, you have to have a changing flux. Direct currents have a constant flux, so you would not be able to produce an EMF on the other side with the direct currents. Number 35, a conducting bar with vertices PQRS is moving vertically downwards, so let's call it like that, with constant velocity v through a horizontal magnetic field B that is directed into the plane of the page. Okay. Which side of the bar will have the greatest density of electrons? Well, first, imagine that you have a positive charge on the bar. It's going downwards. There's field into the page. So the force on this positive charge will be to the right. That means electrons are moving to the other side, to the left. The answer should be PS or SP. Number 36. A circuit consists of 3 identical capacitors of capacitance C and a battery of voltage V. 2 capacitors are connected in parallel with a third in series. The capacitors are fully charged. What is the charge stored in capacitors X and Z? Okay, number 1. Let's get the total capacitance. And in order to get the total capacitance, first we have to get the capacitance of the ones in parallel. When you have a parallel, you have C, C, just add them up. Let's call this CP for parallel is 2C. So 1 over total is 1 over the capacitance of Z plus 1 over the capacitance in parallel, which is 1 over C plus 1 over 2C. With a little bit of math, you can find the total capacitance as being 2/3 C. Notice because of this equation, the total capacitance is smaller than 1, see, which is smaller than either one of the individual ones. Okay. Second, let's get the total charge. The total charge is the voltage times the total capacitance. Okay. In this case, total capacitance was 2/3 C. And here you have to know that if they are in series, the voltage is different and they add up to the total. But if the voltage is different, the charges are the same. The charge of everything here is going to be the same, 3 over 2C. So we have for Z, 3 over 2, 3 over 2, CV. Forgot the V there. Okay. What about X? Well, together X and Y do have a total 2 over 3. But individually, they only have half each. Because if they are in parallel, they have the same voltage, but they have different charges that add up to the total. They each have half, so 1/2 of 2/3 is just 1/3, which would be either C or A. The answer is, of course, C. Number 37. 3 correct statements about the behavior of electrons are, I'm not sure if they should have added the word correct. Just 3 statements. 1. An electron beam is used to investigate the structure of crystals. An electron beam produces a pattern of fringes when sent through 2 narrow parallel slits. Electromagnetic radiation ejects electrons from a surface of a metal. Oh, actually, they are correct. Which statements are explained using the wave-like properties of electrons? So let's look at this. 1. Electron beams bouncing off crystals behave as waves going through diffraction gratings. They interfere. And you will see, of course, constructive destructive interference, which only occurs if there's a wave. So that is okay. 2. An electron beam produces a pattern of fringes when sent through 2 narrow parallel slits. Again, the fringes imply wave interference. So it's, yes, the wave-like properties of electrons. And 3. Electromagnetic radiation ejects electrons from the surface of the metal. If you recall, yes, electromagnetic radiation is light, which has wave properties because it interferes, but the reason the electrons are ejected is because of photons. And photons are a particle behavior, which is not a wave behavior. So only 1 and 2 are wave-like behaviors, even though number 3 is correct. It's not about waves, it's about particles. Number 38. Samples of 2 radioactive nucleates X and Y are held in a container. The number of particles of X is half the number of particles of Y. So let's write that down first. Number of particles of X is 1/2 the number of particles of Y. The half-life of X is twice the half-life of Y. So half-life of X is 2 times the half-life of Y. The question is, what is the value of the activity of X and over the activity of Y? To get this, activity is decay constant times the number of particles. And we just have to put activity of X, number of particles of X, decay constant of X. Then activity of Y is decay constant of Y and the number of particles of Y. But the decay constant is not the same as the half-life. In order to find the decay constant, you have to get the natural log of 2 over the half-life. Which means that decay constant of X is 1/2, no, twice, the constant of Y. Because Y has 2 times the half-life, so it has 1/2 decay constant. So let's put this in this here. This would be 1/2 decay constant of Y and 1/2 number of particles of Y. This cancels out. The answer should be simply 1/4 because of 1/2 here and here, and these come from this part and this part here. Number 39. The dashed line represents the variation with incident electromagnetic frequency F of the kinetic energy of the photoelectrons ejected from a metal surface. The metal surface is then replaced with one that requires less energy to remove an electron from the surface. Which graph of the variation of the kinetic energy with F will be observed? So first, if you forgot about this, the energy of the photon is going to be divided and be used in 2 things. First, it will be used as kinetic energy, and it will be used to escape the metal. This energy required to escape the metal is called the work function. So if you have enough energy, you pay for the energy to escape, and whatever is left over becomes kinetic energy. The energy of the photon is Planck's constant times the frequency. Well, the kinetic energy is just the kinetic energy. And the work function is just the work function, the amount of energy required. So in this graph, the kinetic energy is the y-axis. So let's put the kinetic energy on the left. The frequency is the x-axis. So you put negative HF and minus the work function. This is in the form y equals mx plus b. H is the slope, which is Planck constant, and the work function, which is the energy required to escape, is the y-intercept. The Planck constant, being the slope, is important. The slope does not change. Doesn't matter if you change the metal. So if this was original, the only possible answers would be either A or D. You cannot change the slopes. Second, let's see what happens to the y-intercept if you just continue this graph down there. First, you have some amount of energy required to escape metal, the metal here, the original metal. And A requires less energy and D requires more energy, which means the answer should be A. Finally, the last question, number 40, it says, which graph shows a possible probability density function, absolute value psi squared, which is equal to the probability over the volume for a given wave function psi of an electron. Okay, so first of all, if you have any wave function, it's just a wave function, of course, it can be a complex number, but if you ignore that fact, if you get the absolute value and you square it, you cannot get negative values. So not negative, it cannot be A or B. Now, the only difference between C and D is that there's distance and time here. And what you should notice is you're trying to find the electron in a space. Here, the probability is using, well, space, right? The distance. You're looking through space, not time. So you have a distance here, and you try to find where it is. You're not trying to find it through time, so it cannot be D. At least for this specific case, if you had a function that tried to find it with time, and you have a, interval of time you want to find it, you would probably be D, but in this case, it's just C. And that's it. Thank you for watching, and see you next time.